So in this chapter, we'll look at motion along a straight line. Um, so we'll define these various quantities: position, displacement, and motion of an object, and all these other quantities. So here's a typical motion we'll see. Here's an object, and it'll be constrained to move along a straight line. Ultimately, we'll be interested in motion in 3 dimensions, but it turns out that motion along each axis is independent of the motion along an orthogonal axis. So we will look at the motion of this object now. So for instance, this car is moves forward and then starts moving backwards. Okay, so the position of the car, we'll call this the x-axis. Here the origin, that's the reference point, and distances to the right are positive and distances to the left are negative. Okay, so the position of this car as a function of time, so the x coordinate as a function of time is plotted on this graph. So what this graph tells you is at x equal to 0, at t equal to 0, the car is at 30 meters. At 10 seconds, it's at 50 meters. At 20 seconds, it's at 38 meters or something like that. At 30 seconds, it's at 0 meters. At 40 seconds, it's at minus 40 meters. And at 50 seconds, it's at minus 50 meters. Anyway, this graph, this position as a function of time, gives you the location of the object at all times. Okay, and so this graph contains all the information about the motion of the object, and that's what we're looking at. So, and this is the useful description. Well, if you have the position as a function of time, then you know everything there is to know about the motion. Okay, so you can go to this link and simulate that motion. The iPad doesn't allow me to simulate a Flash program, Flash simulation. So, um, so we'll consider motions of particles or objects that move like a particle. So we are treating this like a particle, since every point on the object moves with the same velocity and so on. So you could treat it as a point particle. Later we'll learn that forces cause change in motion, but we'll consider that later, and that's the subject of dynamics. Um, so right now we are only interested in in describing motions. And as you saw in physics, we have quantities that are vectors and quantities that are represented by scalars. So velocity is a vector, force is a vector, acceleration is a vector, and so on. Temperature, pressure, speed, and all those things are scalars. In one dimension, vector, so here's a displacement vector. A vector can either point to the right or to the left. Okay, so in 1D, the sign of the vector quantity represents its direction. So this displacement could be this, let's say this displacement is plus 20 meters and this displacement is minus 20 meters. So the sign tells you the direction of the vector. All right. So as we saw, so for instance, here is another motion. Here is an armadillo walking back and forth along the x-axis, and its position its x coordinate as a function of time is given by this graph. So this graph tells you where the armadillo is at all times. So you can choose, if you ask where is it at 1 second, there it is at minus 4 meters. At 3 seconds, it's at the origin, and so on. So a position time graph is a graphical representation of the motion. So here's another position versus time graph. So for instance, in this graph, this is the position of some object in kilometers. For the first 10 minutes, the object is moving to the right, and then for the next 10 minutes, it's moving back to the left, and then again to the right, and then back to the left. Okay. Displacement, the displacement vector between two instants is just the vector pointing from the initial position to the final position. And the displacement vector is given by delta x. It's the final position vector minus the initial position vector. So for instance, on this graph, the displacement vector would be, if the object is here initially and there finally, that would be the displacement. And for these two times, that would be the displacement. So anyway, this is the displacement vector. Distance is a scalar, and it's the total distance traveled. So if, for instance, if this car starts off here, goes there, and then goes back over there, so for instance, um, so if it goes from here to there, the displacement will be that vector. But you can see that the total distance traveled will be a lot longer. So distance, a scalar, is the length of the path covered by the particle. One of the things we're interested in is the average velocity. Average velocity is a vector, and it's defined as the displacement divided by the time over which this displacement happened. And it's so on this graph, on the graph, it looks like so. So here's position versus time. If you wanted the average velocity between these two times, there's the initial position, there's the final position, it would be the slope of this line. That would be the average velocity. Between this time and that time, the average velocity would be the slope of this line. Okay. Average speed is the distance traveled divided by time. Okay, so in this graph, let's say the car starts here, goes there, and then goes back there from A to F. The total distance traveled would be 30 to 50, 20 meters, and then 50 to minus 50, that's 100 meters. That would be 120 meters, so that's what would go in there. Total distance traveled divided by time. Now, neither average velocity or speed provide details of the trip. So you can have an infinite number of different trips which can have the same average velocity or speed. So the average quantities do not provide details of the motion. And by the way, average speed and average velocity are not related. Okay. It's only, you'll learn in a second, for instantaneous velocity, the magnitude of instantaneous velocity is the instantaneous speed. Only in that case are they related. So here we go, we'll define instantaneous velocity. So instantaneous velocity is defined as, here's the average velocity. In the limit delta t going to 0 of average velocity is instantaneous velocity. And that's the time derivative of the position. Okay, so again, like I said, if you have a graphical, so here's a graphical representation of an object's position as a function of time. This is a complete description of the motion. An alternate way of doing that is, I'm just making this up, is a motion, giving the position as a function of time. So here's another motion. So this is a complete description of a motion. Okay. All right, let's, so velocity would be time derivative of the position. So in this, for this motion, the velocity would, as a function of time, would be given by 10t plus 7. Okay. All right, so let's pause here.